We were discussing last time about branch prediction, and we were talking about the basic mechanism of prediction. And we are talking about two techniques. One is just to look at the branch by itself, trying to identify the branch by a number of bits from the program counter. And the other one was looking to what we call the global history, then to the current branch, but also to branches which were executed before, due to the fact that we observe some correlation between branches. Now, what you see in those diagrams, which are, very much loved by the computer architects, if you read a computer architecture paper and you don't see those, not good. The reason why it's not good is because the way we do business is you run programs on simulation base, on FPGA, on whatever. You collect statistics on different programs, like you see here, there are a couple of benchmarks. And then you make this diagram, and then you try to figure out what do they tell you. There is a tendency of some people are making them and they don't comment, which is not good. The key is to try to understand what those diagrams are telling you. And what we have here, there are three predictors. Then it's the execution on a certain architecture. I don't really care about the architecture. But in that architecture, I have prediction. The red one has 4 kilo entries in the branch prediction table, in the branch history table, with 2 bits per entry. And this is the misprediction rate. Good morning. And per benchmark is different. You see, just look at the red. Then some benchmarks are behaving nicer, some benchmarks are a bit more nasty. Then you see the first benchmark, there are close to none, on matrix is close to none, you could have closed the door,
Oh, it was already open.
Yeah, but it was not the idea that I'm inviting you in.
All right.
The student who entered before you, let it open. I don't care to have it open, but sometimes people on the corridor, they make noise, they play football, they have fun in life. Not like for you. Okay. I'm friendly and I understand that you are coming late, but try to be on time. At least try, right? I'm not criticizing you because you are here. But that's usually the misery of life. The one which is not guilty is getting all the, the criticism. Then, if we look at this kind of bars, we see that the misprediction goes from 0 up to 16%. Then, on the benchmark, which is called AQN EOT, the predictor is doing very bad. Okay, then it was not that I lost popularity, it's just that the timing is slightly different today, and there is a problem with the door as well. No, there is somebody else coming. Now, I look at what I could essentially get with such prediction, assuming that I can invest infinite amount of resources, which means that I will never have branch aliasing. And this is the next predictor, which is not something that I can implement. I don't think you stay good there. Hello? It's not a good position there, because you will have to look like that. It's not that I mind that you get close, but it's better for you. Then this is not an implementable predictor, but this is telling me something about the upper bound that such a predictor, organized logically in this way, can give me. And what I see is that unlimited entries I can use as many as I want, will not give me much better than somehow 4 kilo entries. It's performing almost all the time as good as the limited one. Now, this is a good indication because it's telling me about what can I hope for. Then I cannot try to get better than that with such a scheme because I cannot invest more than infinity, even though that it's only potential. Now the third predictor, it's changing the paradigm. I'm having the same amount of resources, but I'm using them in a different way. Then I take the 4 kilo entry resources and I organize them in 4 banks. And I do a prediction based on local and global history. Then from the hardware investment point of view, I'm the same. But let us look on what I get with the same investment. Then on the blue bar, you see that almost all the time, I'm doing better on blue. Then same investment, different paradigm, is doing better. Now there is one small problem here. If I look at GCC, which is kind of representative for application and operating system, the performance is kind of the same as the infinite predictor. Then I'm not doing better. But still, this is an implementable solution, while the other one with infinite resources is just something which it's in my mind. Then it's a simulation artifact, but not in the wrong sense. In simulation, I can do that. I invest resources in the limit of the memory of my computer, of my network cluster, whatever. Then what I can summarize from the previous slide is kind of here. And I told you, the only thing which I didn't tell you is the source of the misprediction. But somehow we discussed on that. You know, it's the fact that I may have aliasing on branches, that I am making a prediction based on a behavior of another branch than the one that I'm looking at, due to the fact that I'm using a limit in the amount of bits in recognizing a branch. And essentially speaking, I can deduce, or I can conclude that it's good to use local and global history because this is increasing the accuracy. Now, sometime, let's say when I am in a loop, the local history is more relevant. Sometime when I'm not in the loop, the global history might be more relevant. And for that reason, somebody came with an idea and said, let us mix them. Which means I am doing predictions with a good local predictor and a good global predictor in parallel, kind of using different techniques. And then I have somebody which is, let's say, the boss, a kind of controller, which is saying, it's looking at them and is saying, who was right, you or you? The one which was right is getting the credit. If you are wrong once, you still get the credit. If you are wrong twice, the other one will get the credit. Then it's the same principle as the 2-bit prediction, which is giving you the benefit of the doubt. Then you are wrong once, it's okay. You're wrong second time, you will be penalized. I mean, I'm speaking in general, but in this case, it will be switched. The same principle is now for predictor 1 and predictor 2. They are working on a different kind of strategy. As I said, they usually are, one is local, one is global. But this is a paradigm which you can apply on any type of predictor. And the power of the paradigm is coming from diversity. This is something which is very important in general, and today it's even more important due to reliability issues. If you have, let's say, a very important block in your system, like, you know, we speak about airplanes, we were talking before about going over Ukraine, which the system could not protect you on that, but we are speaking about an automated pilot maybe. Because this is very important, what you do is you use modular redundancy. Then you implement the pilot in 3 versions, and then you use a voting system, and the majority will win. It's like in democracy. Now, because different type of implementations may be affected by different type of aggressions, it's good to use diversity. Then you make one implementation in a certain technology, another one in another technology, another one maybe based on another algorithm. The same story is here. Diversity can help you, and if you are able to choose the right source in a proper way, then you win. Okay, now the story with French prediction, it's over. And I will just say something, but not much, about an extension of the instruction set, which most of the modern processors do have in order to avoid branches. Now, you do not treat them as branches, you do not have branches, but still the control hazard, the decision is there. This is called conditional execution or predicated execution. Then you add an extra operand to the instruction, and if that operand assumes a certain value, the instruction will be executed. Otherwise, it will be a no. Then nothing will happen. Why is that good? Because I'm not creating any kind of problems with decision. I don't have to predict branches. I'm just executing an instruction, and if the condition for the instruction is okay, it will execute. Here we have an example. If R1 is 0, then R2 is equal R3. And that instruction is called conditional move on 0, and the condition is on R1. If R1 is 0, that move will happen. Then the content of R3 will be moved in R2. Otherwise, the processor will do a NOP. Now, doing a NOP, it's not exactly something that I would love to do. I would love to execute an instruction, not to do a NOP. But if I want to execute an instruction, I have to make that a branch. Then it's a kind of trade-off in here. And I can implement also some other more complex things. Then you see this is an if-then-else kind of construction. And what you see is that there is a preparation for the if-then-else. Then what I'm doing there is store liter. Then R9 will get a value depending on the comparison between R1 and R2. And now I'm using R9 as the reference in order to execute or not the 2 assignments. Only one of them will execute at a time. What will happen if R1 is equal with R2? What do you think will happen? Come on! It's Thursday. It's not Wednesday. Wednesday it's a bad day. It's too early. Now you are awake. Oh my God. What happens if R1 is equal with R2? R1 is equal to R2. Then that condition, what will happen?
So R9 is going to be 0.
Then it's absorbed in the condition of being like, then it will go on one direction, even on larger or on smaller. It's not explicitly treated the case when they are equal. And it's not clear from this description what will happen in that case. But it will be absorbed on one or the other. Because you know, when they are equal, according to the normal definition, the R1 smaller than R2 cannot assume any value. Or not. It's a matter of convention. This is what I'm trying to explain you. Because you may imagine that if they are equal, this will get a 0 or a 1. Then you have to check in the description of the architecture the behavior of that instruction. The one which defined the architecture will tell you exactly what will happen. Not all the time it's obvious from what is going on there. Now, this is nice. You get rid of the branches. You don't have to do prediction, but you will have to do a bit of complex work around the instruction because you have to check that condition. Okay. Now I can say that we essentially know everything about fast computers and how to speculate instruction level parallelism. Then I can go home, kiss you goodbye, right? Now, unfortunately, you will have to listen me further, and we'll discuss about how to put those things together. Because we know how to do branch prediction, we know how to do dynamic scheduling. Tomasulo taught us how to do that. And we also know in principle what speculation means. Because there are two approaches in here. I can make a branch prediction, and I can start fetching on that direction, and I stop after fetching. I'm not really executing in that direction, but I also can start executing in that direction. There are, let's say, pluses and minuses in both cases. Then if I make a branch prediction and I start fetching, if I are right, I am prepared for the execution in that direction. If I'm wrong, I have to reverse. If I am starting also the execution in that direction, assuming that I have enough functional units to keep busy, I will win a lot if I'm right. But if my prediction was wrong, I have to undo a lot of things. And I also have to be careful on not damaging the status of the processor. Now, as you probably can guess, speculation is the right way to explore the instruction level parallelism. Because when I speculate, I'm extending my scope of the instructions that I can execute in parallel. If I am in a small branch, we said 3 to 6 instructions, there are not very many. If I'm going beyond the branch, I may have other 3 to 6, and maybe I can speculate. Modern processors do speculate on more than one branch at a time. The complexity may get out of our imagination in the sense that it will be a bit hard to grasp what's going on, but the concepts are very much the same. It's nothing changing fundamentally. The only difference is in the amount of complexity that you add in the processor in order to deal with more things at a time. Okay. Now, there is something on speculation which you have to be sure you are doing in a proper way. And this is the commit of the instruction. If you speculate and you execute in a speculative mode instructions, that's fine. You keep your functional units busy and you take advantage of the available hardware, and then you increase your performance. The point is not to commit an instruction if it was executed in a speculative mode. If you do that, you update the status of the processor. You change the value in the register file. You change flags related to the status of the, I don't know, like sign or the control status register of the floating point units and things like that. You are trying to keep that as accurate as possible. When the branch was solved, which may happen, you know, eventually later, what you do is you say, okay, this branch was solved and was taken as I predicted. Then I look in what is called now a reordering buffer, which you can see again a bit like a reservation station, but it's slightly different. And I look in the reordering buffer and I'm saying, which instruction was executed in a speculative mode related to this branch? This and this and this. Okay, then I can commit them. I can put them in write back, update the status, and continue. If the branch was predicted taken, but it was not taken, what I will do is I will take all those instructions which are executed in a speculative mode, I will throw them away, I will clean the pipeline, and I will start now the execution in the other direction. Then you see, the more I go ahead, the faster I am, the more aggressive I am. But if I'm wrong, the penalty is also big. Then for that reason, we always have to make a balance between the speculation level, the certainty that we have on prediction, and things like that. Now, that's kind of misery in life. There is no win-win situation. Or it is. What do you think? You don't want to talk with me? What do you think? Is there win-win situation in life? You never thought about that. Or you did, but you don't want to tell. Okay. Now, how do I do that? Actually, what I'm doing is I'm fetching instruction, I'm decoding them. This is happening in order. Then I'm spreading instructions to the functional units which I have available. You see, I have different pipelines here if you want. This is a typical structure. Then I have the ALU, which is solving arithmetic logic units, including maybe address calculation. I have memory, I have floating point, and I have branch. And then those instructions can execute in parallel. On dispatch an issue, I have to do Tomasulo kind of work. Okay? Then they go on different avenues, and eventually they hit, you know, the reorder buffer. The reorder buffer is a temporary storage. Some instructions which are there will be committed, others will be thrown to the same. And the instruction fetch and decode and the write back are done in order. And this is solving a couple of issues, including the fact that I'm having precise interrupts. Okay? Then I speculate, but I correct if I'm wrong by processing the reordering buffer. Now, one of the important things in having speed up is to have processes which are decoupled, as I told you also in Tomasulo. There are, you know, it's the issue process which is working, and there is the execution process which is working. They are decoupled. In the same way, I have also the commit process now, which will commit instructions which are there based on the outcome of the branch which were predicted in the past. Which means I should be able to do my own bookkeeping. If a branch is committed or not, I have to know which branch was that. And here I cannot allow for aliasing. And I have to know for sure that that branch was the one which is attached to that instruction. If I have an aliasing here, my processor will not execute correct the program.
I just have a question.
Sure.
The previous figure, is there a reason why the memory and the floating point modules are in series? Or is
This
it-
is their pipeline. Then I'm assuming that the instruction, then a load store will take 2 cycles, a floating point instruction will take 3 cycles, an ALU is 1 cycle, and a branch is 1 cycle. But this is just an example. You know. The artist which did that put that many. Then, now, we have the ingredients on doing this, and this is kind of, you know, the summary of what we can do. And the conclusion is that when we talk about hazards, there are structural hazards which I cannot do anything about them after design, but I can do things at design time. And in order to do that, I have to run experiments, to run simulations, to try to understand what's going on in my architecture and which decisions will, you know, give me benefits or not. And there are the true data dependencies which I cannot fight with, because those are true data dependencies, and I cannot start an instruction before I know the result of the previous instruction. Okay, this is what we know thus far. Actually, I can also make prediction on the result of the previous instruction. If I can do that, I can also kill data dependencies. The question is, can I do that easy? And if my previous instruction is an addition, in order to make prediction over the result of the addition, what do I have to do the addition? Or maybe to have a table where I have the value of the operands and store the pre-calculated result. Sure, things can be done, and you know, only the sky is the limit. The question is how much I invest and how much I get back. Okay, now.
I have a question regarding this graph.
Which one?
The 2,2 is the tournament thing, right?
Yes. No. No. That's local global combination. The one which has 2 bits to predict the local branch,
Yeah.
and 2 other bits to see how the previous branches are behaving.
What wasn't that tournament?
No. That's the tournament.
Yeah, I thought this.
No.
That was
This one. That's 2.2. Then I have 4 predictors, and each predictor will be chosen depending on how the previous 2 branches were doing. Like in this case, the previous branches were 0, 1, not taken. Then I look on this one, and that will give me the prediction. Okay. Let's see what else we have. Now we'll go further and we'll discuss about how to use those basic techniques in a more innovative way to even push further the instruction level for our tools. I was not the artist. Then the slides were done by a previous PhD student. Okay, Then we'll talk about how to increase the performance by increasing the issue rate. Then instead of issuing 1 instruction per cycle, to issue more instructions per cycle. Then, and modern processors do have that. They issue 4 issue, 8 issue, 8 instruction. Okay, and try to understand what are the consequences of that from the hardware point of view, and what do they pay us back in performance, okay? Now, this is very nice, this is very intuitive, you know, old cars. What car is that?
Volkswagen. Volkswagen?
I don't know, I think it's a 2 chevaux. You know the Citroën, the old Citroën? 2 horses, 2 CV, which in French is 2 chevaux, 2 horses. No, you don't know it? No, it's a beautiful car. It's still running. Then, pipeline, you stay in queue. Dynamically scheduled, you can pass. Then we discuss. Now, this is the real highway. Then here we have a superscalar processor which can actually issue instructions in a wider base. Then if I have a lot of resources, and because we discussed about technology and we said transistors we have a lot, then I have a lot of functional units. The question is, how do I feed them? And in order to feed them, I will use whatever I know, but there are some complications. In order to select candidates for issuing, I have to have a larger window on the instructions to choose, instructions that I can execute. If I don't have a larger window on the program, I will not have candidates for execution. Then my hardware will die of starvation. This is easy said, but it has a lot of complications and consequences on the way the processor is organized. And we will talk about that. Now, essentially, you guys, if you have a conversation, I will welcome you outside. Not that I don't want to disturb you. Then there are 2 basic flavors of that kind of multiple issue processors. And some are called superscalar, the other one are called VLIW. From the point of view of what they do, things are the same. What they do is they take a bunch of instructions and they dispatch them to the functional units, each cycle. The difference is on how you select that bunch of instructions. And there are essentially 2 flavors of superscalar and 1 very long instruction word. Now let us start with VLIW. VLIW means the following. The compiler is looking at the code and will pack instructions in groups, will cluster instructions in groups which are executable in parallel, and the dimension of the group will depend on the available functional units. Then the compilers know exactly how many functional units I have in the system, and instead of issuing 1 instruction, it will issue 1 mega instruction. And let me try to. Let us assume that I have a bunch of functional units, more than 1 ALU, 1 multiplier, whatever, and that each of those has an instruction, typical instruction, code, operands, whatever. Now, what this machine is doing, it's saying, I don't want to spend energy and effort to try to find the instructions that I'm issuing in parallel at runtime. I will invest in a compiler which will run maybe 1 day, and the compiler will give me now the code in long instructions. And then we'll try to fill those slots. Then I assume that this is a 4-way issue machine. Then I can execute 4 instructions in parallel. And I can also say that this and this are dedicated to ALU instructions. This is memory, and this is floating point, hypothetically. Which means that if the architect decided to do that, my machine can execute 2 ALU, 1 memory, and 1 floating point in parallel, in the sense that I can issue them in parallel. Now I can execute more because those may be pipeline. But from the feeding point of view, I can do that. Now, the compiler will look on the code and will try to fill those slots. If they are not available, all of them for execution, I might put here a no. Because this is the best I can do. Okay? Now, the advantage of this solution is that no energy and time will be spent at runtime for the scheduling of the instruction. There is no real dynamic scheduling going on. It's just the effort of the compiler to find instructions which are in parallel and to create a code. Then now when I fetch from the memory, I have to fetch, that kind of long instructions. Or I can fetch short instructions, but I have to pack them. Because when I'm executing, this will be dispatched to the hardware as an entire. If there is a problem, because I still have to check the structural hazards, the compiler is not aware about things which are going on dynamically at execution time, then the compiler can decide that from the static point of view, this is an issuable instruction, but the status of my processor may say that this is not some kind of memory, port memories and things like that may preclude it. Then when I have such a situation, the entire package will stop. Then this is going like a package, all together or none. Wait for the next thing. Now, those are essentially architectures which are utilized. This was proposed by Hewlett-Packard. You heard about Hewlett-Packard, I hope, or not?
Is that the founder of Hewlett-Packard?
Yeah, the company, Hewlett-Packard, the old one, from all times. They are also famous for instruments, for oscilloscopes and things like that. I don't know if you ever, logic analyzers, yes.
So in this kind of architecture, right, we have two ALUs,
Mm-hmm.
and if their data depends, the compiler has to make sure there are
No. This is something that the compiler will create this based on parallelism. Then it has to check whether or not these two values do not have a data dependency. If they have a data dependency, they cannot be placed in the same package. That's one story. Then the true data dependencies are checked by the compiler. The goal of the compiler is actually to fill those in all the time. In practice, this will not happen due to the nature of the application. At runtime, however, even though there is no data dependency, here I may have a structural hazard in the machine, which may preclude the issue of this as an entire. Let's say I have a problem with the memory from a previous instruction, which will take slightly longer, and I do not have ports. I have a condition here. This will be checked at runtime. Then scheduling of the instruction is done statically by the compiler, and they are packed in mega instructions or very long instructions. Structural hazards are checked at runtime by hardware. Then it's not that I'm not doing any work. There is no way to issue more than one instruction at a time without doing checks. Now, this is digital signal processor, essentially the most famous used to be Primedia, which is a Dutch product, right? Dutch people should be very proud of. Unfortunately, Philips is out of the business with TVs and things like that. It's going after the money. Lighting and medical, it's paying better than consumer electronics. That's life. Now, if you start from this, what you see is that maybe there is a problem which precludes me of issuing the package, but maybe most of the instructions are actually issuable. And this is the way the superscalar statically scheduled is working. Okay? I started from the bottom and I will go to the top and then to the middle, from the reason that I'm trying to provide you things in a kind of order which I like, but it might not be the one that you like. Okay? Now, the statically scheduled superscalar, it's kind of a strange construction. When you think superscalar, means that it's something which is more than scalar, right? Then it's vector. Statically scheduled, it's counterintuitive because we will keep on talking about dynamically scheduling instruction. Statically scheduled superscalar, it's a compromise. I'm trying to issue more instructions in parallel. I'm trying to rely on the compiler in order to limit the overhead at runtime, but I'm also trying to fix this problem which precludes me of executing the entire when one is missing. One cannot be executed. Then the statically scheduled superscalar is getting from the compiler instructions in packages. You can see them as in packages. Most of the time those machines are two-way machines, maybe four-way machines, but most of the time they are two-way machines. They are not very parallel. And what is happening is that the instructions are coming in pairs. From the compiler point of view, they are okay. The hazards are checked at runtime, and if one of them is okay and the other one is not, the one that is okay can jump over the one which is not okay. Then I am kind of relaxing this condition. Now this is a compromise and it is utilized in some cases. And the real superscalar dynamically scheduled machine is the one where you have all the freedom. Then compiler is not doing the job, the hardware is doing the job, and it's changing all the things at runtime, which means full flexibility, full freedom, a lot of investment in hardware. High performance, more energy. Okay? Now, it's your legal right, which I have to respect, right?